hopefully you had a very happily Eid. And what we are up today. Okay, so I think so we have 2 lectures left and somehow something like that. And we already have taken something last time, but I'm not sure about to what level did you grasp everything from last time. So I'm going to go very quickly to the chapter number 11 that we have went through. Sorry, chapter 12. I call it chapter 12 because it's from another material of process safety. As I told you, like I could have covered fault mode effect analysis, reliability engineering, which is part of quality assurance, without any example of chemical engineering. But I think so it always will have a better flavor if I apply it to chemical engineering. So just a quick view of it. So last time we went through the risk assessment, and I'm going to be quick because we already have taken these things. And we had mentioned that doing the part of the risk analysis is to multiply the frequency with the consequence. And here the frequency, that means معناته if you have something that happens many times, you need to have an eye on it, right? If it fails many times, you need to have an eye on it. Or if it fails, even if it happens once, but it could destroy everything, which means a very high consequence, you need to have an eye on it. Now, if you have something that is very frequent and has a high consequence, that is a big danger. And this is where we started calculating the risk, where frequency multiply the consequence, okay? So a high consequence makes a high risk, or a high frequency makes a high risk. And to calculate the risk, we multiply the frequency, the consequence. Now, how much you have something in hand to operate this? If you don't know what is the operation discipline, that means you don't know your safety procedures is good or bad, you just put 1. But if you know if it's bad, you put less than 1, all right? And you just go lower and lower than 1. So 1 is the maximum, okay? 1 is the maximum that you can go. So if you have the best safety thing, you will have the operation discipline is equal to 1. So we already know that, and we went through it. I'm not going to go through it again. So the risk is F multiplied by C, which is frequency multiplied by consequence, divided by the operational discipline. Usually you will always find the equations only the frequency multiplied by the consequence without this OD thing. And the OD thing is just an addition factor in process safety, usually added just to make things more accurate. However, it's rarely used in many parts of industries. Okay, so we already know that, so I already explained this, so I don't need to explain it again. So that was the part of risk. Okay, why did we take that part of risk? Because we need this in our HAZOP studies or risk analysis study. Okay, something else that we need also with something to do with reliability engineering, which is the second part of our course, which is related to how much your system is reliable. And when we say how much a system is reliable, that means how many times does it fail, which is mu here. How many times does it fail? And based on the number of times that it fails per year, I'm going to calculate how much it is reliable. Okay, how much it's reliable. Now, P is the probability of failure, which is the failure probability is written here, which is the opposite of reliability. So the probability of failure, so the probability of failure, if it was 0.1, so I have 0.1 or 10% probable of failure in a certain valve. So there's 10% probability of failure of that valve. Now, how that means how much your valve is reliable? It is 90% reliable. So it's just the subtraction of 1 minus the other part. Okay, so this is what it simply means. Okay, I explained that before with the details, but I'm just explaining the terms again. So reliability is exponential into e to the power minus mu t. Probability is 1 minus e to the power minus mu t. Okay, so the failure probability, again, it goes if we have things that are having an OR gate or having an AND gate, the results will be calculated into two different ways. Okay, so if we are talking about things that are having an OR gate, that means you need to let me put it in this way, because this is the way of how I memorize it. Now, if I talk about reliability and they have an OR gate, I multiply them. Okay, if I talk about an AND gate, I multiply the probabilities. Okay, I'll say that again. So if I have an AND gate, I will calculate the probabilities and multiply them. If I have an OR gate, I calculate the reliability and multiply them. It's easier for me to memorize. But if you want to memorize these two as you want, it depends on you. Now, the details, these are things that you have in the industry. You're very familiar with them. And this is the way of how this is how it shows the calculations of, not the calculation, how many faults per year. And we already can see that the pH meter, for example, has a very high faults number per year. Actually, when you go to the lab and use the pH meter, you will discover that that pH meter fails a lot. And of course, if you have a gas chromatography, in which we already have one in the lab of Mariam Aboud, and you will see that the gas chromatography that we have there, it fails a lot, really, it fails a lot. It fails a lot. In this case, this shows 30 times per year. My God. So that is about, we said that last time, it's about like 3 times per month. That means every 1 to 2 weeks, it fails once. And then we have taken example. This is the example of a reactor. And these are switches. Now, this example of the reactor is showing that, that we have a system of alarm, PIA, the pressure alarm. It's an indicator, it's a pressure indicator, and it is an alarm at the same time. Okay, usually they are separated, but now new instrumentation puts everything together in one piece. Okay, it just looks better as a one piece. Okay, but they are different. They are not one whole thing, and they're 2 different pieces. So here it's put as one piece, PIA, PIA, the pressure, because I have went to Pakistan International Airport once. So while I'm writing PIA, my acronyms goes wrong within my head. So this is pressure indicator analyzer. Okay, and here's the pressure indicator controller, where it takes the action of it takes an action if you have an over pressure, if you have the pressure is really increasing. Now, if you have a reaction here, the gases collect up here, you have an overpressure. What is the solution? Solution is easy, and control, how to control things. Please put less feed, if I have a high pressure, so that I have less reaction here. Another thing is to have the relief valve on, but I can't see any relief valves here at all. So just give me an alarm so that I take an action, so that I can open the outlet here by hand, if I would say. Here the switch, the one with the X is the switch. It will switch on this alarm if we have an overpressure, or in this case, it will switch on the controller if we have an overpressure, and so on. So these are the 2 things. Usually, a controller doesn't have a switch, like it's already connected directly. But if you have a switch, that means it takes an action of like a shutdown system, like it's taking action to that further system at a higher layer. Okay, so this is the system that we have. Why did I explain this? I already explained that before, because I just want to go into the details of some little parts. Why do I go to the details? Because I may bring this in the exam, okay? So that's the story. So if you go to each part, the pressure switch 1, okay, so this is pressure switch 1, this is pressure switch 2. So pressure switch 1, if you go to the table 12.1, which is already in the PowerPoint presentation, so they have the same amount, which is 0.14 faults per year. Alarm indicators given as 0.044, solenoid valve is 0.42. Now, you can calculate the reliability and the probability of each one, which is something simple to do, okay? Because you just take the exponential of the minus this term here, multiplied by the t, which is the time. In this case, it depends on the question. What is the time that we have here? Okay, usually we are talking about 1 year, so that should be simple and straightforward. So what else I need to show you here, because we already covered that. Yes, the mean time between failures. The mean time between failures, after you get the final answer, you just divide, you take the reciprocal 1 divided by mu to give you what is the mean time between failures. The mean time between failures. I think so. This is a straightforward example, and we already explained that. It's not this that I want. Now, for 12.2, we need to look at this figure again in terms of the and or gates in a way that we can read this system in front of us with a more touching example, and we can understand what is going on exactly. And in this case, you know that through event trees. We went through this. I'm going to show you the event tree. So that is an event tree. Okay, that is an event tree here. And of course, it's very difficult to draw this figure. This needs some kind of an experience. So I'm not expecting that you're going to draw the event tree for me here. However, if I give you the event tree, I'm expecting that you can calculate the probability, you can calculate the reliability of the whole system. And this is what we want to get to. So this thing here is an example of how you're trying to calculate using the event tree analysis, where you're going to decide to continue operation or to shut down the system or to do whatever you want to do, depending on what, depending on the reliability information or the probability information that is stated here. Now, these values, how did we calculate these values? I think so you already have taken this. I explained that last time. But this is how it goes. I'll say it very quickly again. So you have 0.99 probability here, and put just 0.01 probability. And then the event tree tells you that if you have a loss of cooling of 1 occurrence per year, and this is how did it identify that. So you have an event of loss of cooling, and then it gave you the value of 0.99. And then you have said that if I'm going to continue operation, that is about 74%, and where you calculate the probability here, either to continue the operation or you want to shut down the system. Now, with all this information that we have here, we already have some information from the top where you start using them, where you have a high temperature alarm alert operator. And this is why we separated the 0.99 and 0.01, we can see here. And here where we have the operator notices high temperature, you have a 25% of failure that the operator will not notice that there is a high temperature. And because of this 25%, you're going to use this 25% to identify the 0.99 to 7.425 and 0.2475, and the 0.25 multiplied by the 0.01 to give me 0.0025, and the rest we have here. And then you're going to look at the operator restarts cooling. Now, after he notices that there is a high temperature, what should the operator do? He should restart the cooling. Now, how do I calculate the next probability stage? So I take the probability, which is 0.25, again, the failure that he could identify. So I multiply 0.25 with 0.2475, and I will get this value of failure. Okay, and this is the value of him noticing it, and you can see that the continued operation, there's a good probability here, but we can have things that will run away, but there's a low probability of things that will run away, which is good, which is really good. Now again, this number here, we will multiply it by 0.25, and we will get 0.01875, and this is the failure. And then you take the rest, which is 0.0075 minus 0.001875 to get the rest. I'm doing the calculations very quickly, just to show you the details of it. How do you calculate it? And of course, you can calculate what is now the shutdown occurrences per year. You just add the numbers where you have shutdown, and what is the runaway occurrences per year, in which a runaway, that means you have no control. You will have the problem falling onto your head, and that is very low occurrence per year, which is okay. Now that is the idea of the event tree, where you can use the event tree. There is something number 3. We already have taken that again in our last lecture, but I'm reviewing things really quickly because I know it had been in Ramadan and had been tough for all of us. The concentration was not as expectation. Okay. So what do we have here? This is an example. I think so. I should have shown this example by its own. This is where you have the fault tree analysis. And let me go outside, and I'll remove this. Okay. Yes. Okay. This is better. Now, I did this just for a better view. So now if you have a flat tire, we already have taken this last time. You have a flat tire, which is the top event, and then you have the intermediate events, and you have the lower events. And here you are saying that simply, if you will have a flat tire because of tire failure, or there's a problem with the road debris. You have a tire failure because of defective tire or worn tire. And here, when you identify the events, you could put more events which are unlikely that will happen, or you know that they will happen. So you can put things that even out of your mind. Why could this happen? Okay, so these are the things that you have here. Now this is an OR gate. You can see this is OR. That means the flat tire will happen because of the tire failure, or it's because of the road. The tire failure will happen because of the defective tire or because of the worn tire. And it's important to know the word or, because sometimes it's and. That means both should happen so that the tire fails. In this case, that is not the case. And this is where you use this and and or gate. The difference between and or, if you have this line here and you have this curved line here. Okay, so, and we already explained that you put a top event where you have the tire problem, or you have the overpressure in the reactor in the next example, and then you put the existing events. That means, why did this happen? What are the conditions of this of the top event happen? Why did the tire become flat? Why did the overpressure happen? Okay. Number 3, what are the events that cause the next event, which are the intermediate events? And then you need information about the physical and information. That means what alarm that do you have? What is your system? What equipment do you have? And then you need some more information about the valves and so on. Now, the example that we have taken was this reactor here. And again, I'm explaining this again because I'm going to give you something similar in the exam, which is different than this, but it will have something similar. Okay, to calculate what? To calculate the reliability of the system, which is part of reliability engineering. Okay, and so this is the system that we have. Now, what does the system tell me? It tells me that I have an overpressure, and because of the overpressure, I will have this AND gate, which tells me that the reactor will be overpressurized because of the failure of the alarm indicator. Okay, failure of the alarm indicator, that means this here alarm indicator, that PIA. So failure of alarm indicator or failure of emergency shutdown system, that means failure of this PIC. So failure of this and failure of this will cause the overpressure, because if you have this failing, at least you have that other controller which takes the shutdown, emergency shutdown system, will take an action. Now, if PIC doesn't work, PIA will give an alarm so that we can tell the operator to quickly close this thing or to take an action within the solenoid valve. So in this case, now if PIA and this, both of them fail, definitely you will have an overpressure of reactor. Now, if you have both of them, which is an AND in this case, the next step is to do what? The next step is to ask ourselves, why the alarm indicator will fail? The alarm indicator will fail because of one of those reasons, either because the pressure switch did not, it will fails, or the light indicator fails. So it's either this fails or the light indicator, which means this is working, the switch is working, but the alarm light is not working, so the operator does not see it. So it's either this or that. Similarly, for failure of this PIC that we have here, is either this pressure switch is not working or the indicator of the light. Okay, now, so this is the system that we have. This is the system of that, what we have here. Now, consider that in the exam, of course, this is going to be given to you, the one on the left here. Okay, this is going to be given to you. However, you may not have these details. The details of the probability and reliability, you're going to get them from where? You need to get them from the table. So that's the first thing that you need to know. And of course, the rest are going to be calculated by you. Now, in this case, just to calculate the overall reliability, we need to start from the bottom here. And remember what I said, which is easier. When you have an OR gate, you multiply I always forget that. You multiply the reliabilities. Let me make sure that that was the case that I had in my head. Okay, yes. So if you have an OR gate, it's easier to multiply the reliabilities rather than taking 1 minus P and 1 minus P and multiply them, okay? So whatever you want to do. So in this case, I have the reliability of these two systems, and of course we know how to calculate that. That is equal to the exponential to the power 1 to the power minus mu, which is the volts per year into time. Okay, so I calculate, so I multiply 0.87 to 0.96 to get the answer 0.8352. 1 minus 0.8352 is the P. Now I have here an AND gate. So in the AND gate, it's easier to do what? To multiply that probabilities rather than the reliability. So I multiply 0.1648 with 0.4258 to get 0.0702, and then I will find the reliability, which is 1 minus 0.0702. And the reliability of the system is over 90%, which is good, and which is good enough for us. So that is the reliability of the system. So I think so this is clear and so on.
Doctors,
تفضل.
for example, the question when we calculate the reliability of the system, right?
صح. The question would be calculate the reliability of the system. ممتاز. You're right. You're definitely right. And the next part of the question, which is what are the possible cut sets? What are the possible cut sets for the pressure to be for the reactor to be overpressurized? Now the cut sets, you can do this in your head, or if you want to go step by step as the book is doing it, it depends on you. Now, if you want to do it with our head, simply what you're going to say, well, this will happen, the overpressure will happen if either this and if these two happens. Okay, we already know that, right? But we want to go to the details of the cut sets. So it's not only the failure of alarm indicator. We want to go to the details of the pressure switches and the indicators and so on. So in this case, if I'm going to remove B, I don't mean remove B, but B means what? B means either 1 will happen or 2 will happen. So if 1 will happen or 2 will happen with C, we will going to have the problem of the overpressuring of reactor. So again, so if 1 or 2 will happen, which is B, if 1 or 2 will happen and C, because there's an and here, if 1 or 2 will happen and C, we are going to have overpressuring of reactor. Now I'm going to cut C and say that, well, C means 3 or 4. So I'm going to rephrase. So if 1 or 2 will happen and 3 or 4 will happen, we are going to have overpressure of C. طبعا 1 or 2 and 3 or 4 means what? Means if 1 and 3 will happen, or 1 and 4 will happen, or 2 and 3 will happen, or 2 and 4 will happen, we are going to have what? We are going to have the overpressure of reactor. And this is where this guy started putting these cut sets. And the cut sets, so he says that now A, I'm going to cross A and put B, because I can only replace A with B. If I want to replace B, I'm going to cut B and I'm going to replace it with what? I'm going to replace it with 2 conditions, 1 and 2. However, my 1 and 2 will be repeated with 3 and 4, which is 1, 3, 1, 4, or 2 and 3 and 2 and if you like this way, go ahead. Or you like the other way that I have explained, go ahead with it. Yani it's all about reliability, sorry, the probability and how to calculate the possible connections, the possible yani connections. There's another word that I cannot get in my head. So these are the cut sets. These are the cut sets: 1, 3, 2, 3, 1, 4, and 2 and 4. Now, with these cut sets, these are all the possible cut sets. Which one is the minimal cut set? Minimal cut set. That means the set that I'm going to consider that I need to put more safety precautions. Which one has the least probability? Which one has the highest probability of a failure? Which means which one has the least reliability. Now, to do this, you need to calculate it, of course. If I want to calculate 1 and 3, okay, if 1 and 3 happens, 1 and 3 happens means I need to multiply the probabilities, which is 0.13 multiplied by 0.13, which is equal to 0.0169. Okay, so that is the first one. And then I need to calculate the other cut set. The other cut set is 2 and 3. So if 2 and 3 happen, So if this happens and this happens, we are going to have an overpressure of reactor. So we are going to multiply 0.04 with 0.13. So that is 2 and 3. If you multiply 0.04 with 0.13, you're going to get 0.0052. And again, you're going to calculate for 2 and 3, and then you're going to calculate for 2 and 4. For 1 and 3 and 1 and 4, sorry. So we will calculate 1 and 3, 1 and 4, 2 and 3, 2 and 4. So we are going to calculate for all the cut sets that we already found that they are possible. These are the possible cut sets to have an overpressure. And then the one with the highest probability of failure. So the one with the highest probability of failure tells me that for example, I'll tell you which one is the highest, and you can do the calculation. 1 and 4 is the highest, which is 0.044. Actually, 0.044 is still low, but it is higher than the rest. Okay, it's still higher than the rest. So because 1 and 4 has the highest probability of failure, I may rethink and put more safety precautions for 1 and 4. More safety precautions, يعني يمكن instead of 1 alarm, I put 2 alarms. Okay, so I have a redundancy, and this redundancy will increase the reliability of my system, which means decreases the probability of failure. Why? Because if one fails, the other one will work. And so this is the case that we have here, how to calculate the minimal cut set. I think so this is good enough, and I think so I mentioned, if you go through this video again, you'll find out that I have put 3 questions now, or 4 questions already for the 3 parts of a question for the final exam. Hello, so that is the fault tree analysis. That is the fault tree analysis. Which is good. Oh, and this is what I wanted to cover. Generally, I think so for this chapter. You have other stuff here, but these stuff are good to know. They can help you in the HAZOP study. However, not in the calculations. The calculations are, we're not going to use those a lot in the calculations, but they are going to be helpful for the HAZOP study. Now, this was a recover for what was in chapter 12, okay? I know it was a quick coverage. Well, not quick. Well, I took about 35 minutes to what we have taken last time. Now, what is left? Besides reliability engineering, we have something called fault mode effect analysis. However, I will replace it with something else. I already gave you an indication that last time that I may replace it, and it's the same thing, but it's a replacement. What is the fault mode effect analysis? The fault mode effect analysis simply tells you that I have a failure mode, and this failure, for example, let me give an example. A drill and tap hole. I have a problem with the tap hole. Why did this happen? Because I used an incorrect hole and size and position. Oh my God. Okay, because I use an incorrect hole size and position, this happened. Okay, so this is the problem. When you find the reasons of the problem, you put the reason of the problem here. Now, what is the consequence or the effect of this failure? So what is the effect of you using a hole size position and having a tap hole within your system? What will happen? So this is the consequences, the effects of the failure. Now, this looks exactly like what? This looks exactly like my chapter 11 of the HAZOP study. And I'm going to show it to you. So here we are saying that I have a problem. What is the problem? The motor fails. The agitator, اللي هو الخلاط, the agitator motor fails. Okay, what are the consequences? واحدة واحدة. I'll say it again. So the problem is the loss of agitation. I don't have any stirrer. The stirrer is not working. Why is the stirrer not working? Because the motor failed. What are the consequences of the motor failing? I have unreacted ammonia within my system. So what are my actions to safeguard that this doesn't happen? I will put an alarm and a detector. So what are my actions? So these are my safeguards. What I'm going to do, exactly the actions and safeguards, they go together. I'm going to add an alarm of the system to prevent any loss in agitation in the reactor. So I simply phrase this safeguard. Okay, I simply rephrase this safeguard. Now, this HAZOP analysis looks exactly like what? Like the fault mode effect analysis. But if I'm going to talk only about fault mode effect analysis with examples of this business thing, maybe it will not be very useful to you. Because we have an exact same form of a fault mode effect analysis. However, it is called HAZOP study to do with the hazards. Okay, to do with the hazards. So what we are going to do, we are going to take this 33-page slide. It's a 1-hour lecture where we are going to go to the details of the HAZOP study, where you say that we have a system. What are the hazards in the system? Now, if I know what are the hazards in the system, I want to put some scenario. يعني, what happens if the temperature goes high? What happens if pressure goes high? What happens if the level controller fails? What happens if the valve is not working? Of course, an accident will happen. Now, if this accident will happen, I need to know its probability and its consequence to know what is the risk. And we already know how to calculate the risk. Now, that is the way of how to do it quantitatively. I want to know how to do it qualitatively using the HAZOP study. So we are going to do the HAZOP study in our system here, just to make sure that we have this identification very clearly. The HAZOP study goes here exactly in this hazard identification. This is where the HAZOP study goes. If you want to put more details, you go through the risk calculation. You go to the risk calculation. And then chapter 12, where you start doing more analysis with the risk and identifying the cut sets and so on. I'm not going to study this today. I'm just giving you an idea, and we are going to go through this through our video. We already have a video for that. I'm just giving you the startup, making you prepared for it. It's a 50-minute video, so it's good enough. We can finish it next time. So because I already have some few minutes, so let me use those minutes. So the hazard identification, we are going to use something called the hazard checklist, hazard surveys, HAZOP studies, safety review. So all of these things that we can use for HAZOP study. Now, the HAZOP study here, the one we have here, is the one which looks like the fault mode effect analysis. There is something very close to it called the hazard survey, which is also used in the fault mode analysis, fault mode effect analysis, but we call them hazard surveys. Okay, so these are different terminologies that are different from the fault mode effect analysis terminologies. Don't worry, we are going to take these things again. So, for example, you go to a car dealer, and we already discussed this before. You have a checklist where the car dealer and he checks, or the car service, sorry, and the car service checks oil, engine, air pressure, fluid level, air filter. We already know this, right? So he has a checklist to check all these. So that is the checklist. However, we're not talking about checking these stuff, which could be a hazard for a car. We are talking about hazards in an industry, which is different. But you already know the idea of it. At the end of the day, it's a checklist to tick if we have a hazard or not. However, why should we only tick? So these are only ticks. Can we make it more details instead of ticking, and to have some numbers rather than ticking? Of course, it's always going to be better. In this case, you can see that this is one of the papers used in industry. Okay, these are one of the papers used in industry. So this is their checklist. And so the safety guy goes and he has his checklist, and he goes for the general layout, and he looks at if the areas are properly drained, is always provided, and في مطوف, okay, the place to pass through, firewalls, hazards, underground obstruction. Is there anything that is obstructing? For example, is there access for emergency vehicles? So he goes and makes sure that everything is okay. And then he goes to the buildings. Stairways are okay, escape ways, the fire doors. These are straightforward stuff. Let us go to something that is more enjoyable. The process. Consequence of exposure to operation considered. So here you may put some more details about exposure. To what kind of exposure do you mean? Special fume or dust hoods required. If I go inside a lab and I see a lab within the industry, I mean, okay, and you see those dust hoods or fume hoods are available. Unstable materials properly stored. For example, we use some material in an operation in GPIC, and this material, if you're not going to, there are some materials which are unstable. Okay, let me be very clear. Sometimes we have mercury in GPIC. We don't know from where it comes, and they tell us they don't know where it comes also, exactly from where does it come. So they collect it. How do they store it? Okay, so then you need to think about it. And so on, if you have any explosive conditions within the lab and so on. If you can also, I'm taking something else just to give you more exposure to other examples. Piping, safety showers and baths required. Sprinkler systems required. Sprinkler systems, showers, yani if anyone has something in the lab and he has something affecting his eyes, he needs to wash very quickly. And so it's important to know that. Sprinkler systems, that means if fire goes on, your rashash, sprinkler rashash. So the sprinkles start pouring on water to put off the fire. So you can see that you're just making sure that everything is in place. So this is where we have a checklist, or what I have explained is a checklist. There is something called the hazard surveys. Okay, the hazard surveys. And these hazard surveys, you have two different popular procedures. One is called the fire exposure index, and the other one is called the chemical exposure index, FEI and CEI. And these hazard surveys, they put some rating to the hazards in terms of storing, handling, processing flammable and explosive materials. يعني, let us see an example of this. Again, all this will be explained again, but I think so. I'm increasing the appetite for you to watch this video, because it is interesting to know all of this stuff. Now, this looks exactly like a checklist. Okay, but rather than putting a tick here, we started putting what? We started putting a number. Okay, so it's written here, exothermic chemical. Let me see that. يعني بشكل عام, fire explosion index. This is an information about the hazard and the place. Okay, so plant, ammonium reactor, sitting in Citra. So it's written here, right? And then you go into the details. There are base factors, special process hazards, special factors. Base factors, that means you look at the exothermic chemical reactions. So طبعا, if you go to the ammonia plant, there you have an exothermic chemical reaction. If it is very high exothermic, put a number here. It's from 0.3 to 1.25. So you may think to put a 1 here. Material handling, endothermic process. Do you have any endothermic process? I don't have. 0.2. Material handling and transfer. Do you have clear procedures for that or not? Yes, I have. 0.25. So I'm putting less, huh? I may put a higher penalty fraction, a factor, if I have what? If I don't have good base for all these details. And what will happen? You're going to calculate the total hazardness within this plant. And the total hazardness in this plant tells you if you need to put actions to how to deal with this ammonia plant that you're dealing with. But I know this was very quick. On Thursday, we are going to take the next lecture. And the next lecture we are going to take is it's called chapter number 12. It's here. You're going to find it on YouTube. So risk assessment, it's called risk assessment. And sorry, we already finished that. We are going to take the chapter number 11, which is hazards identification, which is very similar to fault mode. But instead of saying fault, we are saying hazard. Okay, and instead of saying how did this fault happen, what are the consequences of the fault, we are saying that how did this hazard happen and what are the consequences of that hazard. Fault mode effect analysis gives you tools, table, so that you can use. Those tables, we call them HAZOP studies, or we call them HAZOP surveys. And it's not or and, we call them hazard surveys, and we call them hazard checklists. The word checklist is very similar between both fault mode effect analysis, the FMEA, and the hazard identification. The word survey is still very similar. However, HAZOP study is something that is more specialized. Till here, I'm going to stop. We're going to take the next 47 minutes video next time, inshallah. And by that, we're going to finish with our material. That will be the end of all our material for this semester. Any questions? Sorry, I have taken 2 minutes more. يعطيكم العافية. I hope you enjoyed it, and the little tweak I did for fault mode effect analysis and putting HAZOP as a replacement, I think so it was a good idea, to my opinion. Sorry for that, because this is not written exactly in the course syllabus. It was written fault analysis. I already gave you fault tree analysis. But I gave it to you in terms of what is in the industry, and I will give you the fault mode effect analysis also in terms of industry. I hope this is very valuable to you. الحمد لله رب العالمين. يعطيكم العافية. Thank you very much. See you inshallah on Thursday. يلا فوالله مع السلامة.